In the last 25 years, we've pieced together a model of the universe that describes its origin and its evolution. This is a pretty audacious undertaking, so you won't be surprised to hear that we haven't cracked the cosmic code quite yet. By looking up at the sky at the largest scales that we can see, we've discovered deep holes in our understanding of fundamental physics at the smallest scales. So to solve this cosmic mystery, we need to look at this puzzle from many different viewpoints and many different directions. To do this, we are building a multifaceted toolbox that combines data from huge new astronomical observatories with the latest advances in AI technologies and also complementary information from laboratory experiments. In the next hour, I'm going to show you some of the latest developments that I'm most excited about personally. And I'm going to illustrate them with some cool demonstrations. So hopefully we'll have a lot of fun. And to start, we want to go back into a journey into the past. So please bring down the lights. So I want to start with the most basic point. What makes cosmology work? Cosmology is possible because light has a speed limit. It's very fast, but it's finite, because light takes time to travel to us, even from the nearest stars. We see those stars as they were in the past. So observing the distant universe is a kind of time travel. So when we look out into the depths of space, we see the universe as it was in the past, and it allows us to see how the universe has evolved over time and compare what we see at different times with our cosmological theories. You can roll back time in this way to the most ancient, oldest light we can see, which came into being 13.8 billion years ago. We call this the cosmic microwave background. So this map that you can see behind me was a milestone in the measurement of this oldest light, the cosmic microwave background. It shows a baby picture of the universe. At that time, the universe was only 380,000 years old. That may sound like a very long time to you, but of course, it's 13.8 billion years old now, so it was a baby picture. This picture was made by Planck, an ESA satellite mission. And Planck brought the early universe into very sharp focus. And using this data, we were able to measure the parameters of the cosmological model to pinpoint precision. One example is the age of the universe, which I've just mentioned, a question asked by humanity since the beginning of history. And Planck measured that with 0.5% precision. So we can't do experiments with the universe, right? So I want to give you a flavor of how we use maps like this to learn about the universe. In addition to maps of the sky that we can measure, we also have theories that make predictions for what the sky should look like. We can calculate predictions for universes that are built using different theories with different physical ingredients in them, and they make the sky look different. So then we can compare those predictions with the sky. And so this map is like a fingerprint. And you can identify the right theory by comparing a lot of theories with the data and working out which theories match the data and which don't. So that's what we did. And when we did that, we found something quite surprising. All of the information in the millions of pixels in these maps could be described by just 6 numbers. 3 of those numbers were stuff that we knew about, things like atoms, the fact that the universe is expanding, and that it contains basically a flat geometry in the sky. But 3 of those parameters, those variables, were just unexpected. So I call them like tooth fairies. There's dark matter, there's dark energy, and the very early universe was clumpy. So what made all that stuff in the early universe that grew under the action of gravity into all of the complicated structures we see in the universe today? So these three ingredients are not in our standard theories of particle physics. So we found that the universe was very simple, but also that it was extremely strange. So while we measured these parameters very precisely now, the standard cosmological model remains a phenomenological model. What is the physical nature of dark matter and dark energy? We don't know the answer to those questions yet. They together comprise 95% of the energy budget of the universe. The matter made of atoms like stars and planets and people, everything that is tangible in this room, that's only 5%. So that's really bizarre. We also don't know where all the stuff in the universe came from. So the leading hypothesis for this is that a tiny instant after the Big Bang, a so-called scalar field, which we call the inflaton field, made the size of the universe expand extremely rapidly by a factor of 10 to the power 26. We call this process inflation. This is not what's happening to the economy right now. This is what the universe did back in the day. And at the same time, tiny quantum ripples were occurring in this field. And they got stretched out by the expansion of the universe. And then they are now visible in the cosmic microwave background 380,000 years later. And so these ripples in the distribution of matter in the very early universe then grew under the action of gravity into all of the lovely structures that we see in the universe today. So that's the story. It sounds a bit like science fiction, but that is what we have come to understand. So the starting point of my talk is that the study of the oldest light that we can see in the universe revealed a simple but mysterious universe. And in the rest of my talk, I'm going to give you a flavor of the new tools that we can leverage to try to crack this cosmic code and solve some of these puzzles. So the first approach I'm going to show is mapping dark matter using 1 billion galaxies. So does anyone know when we worked out that there were galaxies outside our own? It wasn't even 100 years ago. Okay, so that's when Edwin Hubble, in October 1923, identified the first Cepheid variable star in the Andromeda galaxy. And that told us that this galaxy is not part of the Milky Way. So why was it so hard to work this thing out? It turns out that measuring distances in an expanding universe is incredibly challenging. So Hubble used an ingenious approach that had been devised by Henrietta Swan-Leavitt in 1912, which is that she noticed that these Cepheid variable stars, they are pulsating stars. So they pulse, they change their size, and their brightness varies as a function of time. So the time for a single pulse, which is its period, that is proportional to its actual brightness. So she worked that out. And so what you can do then is that when you observe one of these stars in the distant universe, you see how bright it actually is, and you see that it is fluctuating in its brightness, so you can measure its period. You know what its intrinsic brightness is. You see how bright it is in the sky, and by comparing those two things, you can work out how far away that star is. So that is still one of the most accurate ways that we have to measure distances in the expanding universe. However, we can use that particular method only in our backyard, as it were, because these stars are not very bright, and so you can't see them out into the very distant universe. So we need some other methods as well, and I'm going to come to that. This is, again, still one of the key challenges we have in trying to understand the evolution of the universe today. So I want to now bring the lights down and show you that This is one of the most beautiful ways that we can study the universe. It is invisible light. There's a reason that our eyes have evolved to view the universe at optical wavelengths, right? The sun has significant radiation output at those wavelengths. So starting in the 1990s, we have been mapping the universe in starlight in very deep and large-scale galaxy surveys. This is part of the Sloan Digital Sky Survey. This is not a simulation. Each one of these galaxies is a real object. There are about 400,000 galaxies in this movie. So for me, the Sloan Digital Sky Survey represents the point when cosmology became a data-driven subject. The full size of this 20-year survey was not huge by modern standards. You can store it in about 40 terabytes. That may sound like quite a lot, but actually even an individual researcher can probably aspire to having that much storage space these days. So it's not very big. But it was a watershed moment for the automatic acquisition of digitized survey data from the sky. So when we map galaxies using light, we can see them arranged in this intricate cosmic web. It's because they're tracing huge filaments of dark matter that you can't actually see. In this image, you can't see 80% of the matter. This is a slice through a simulation of how galaxies trace dark matter. So this one is a simulation of the formation of a cluster of galaxies. So cosmological simulations are a key tool in understanding how the sky surveys that are showing us this data map to our fundamental physics theories. So computer simulations allow us to make detailed predictions for the fingerprints of different cosmological models, just like we did with the cosmic microwave background. These will alter how galaxies are scattered in this underlying scaffolding of dark matter. We can compare those predictions with the data and figure out which of those theories match the data and which don't. So you can bring the lights back up now. So our understanding of how galaxies populate the universe is about to be revolutionized due to major facilities that are about to come online. And cosmologists are gearing up for the torrent of data that's about to hit us. And so we are truly in the era of big tech and big data, and to make sense of that data, we need big algorithms. So the project that I'm personally most excited about is the Vera C. Rubin Observatory's legacy survey of space and time. This is also called LSST for short. LSST is the ultimate big data project. It's going to start taking data in January 2025. The pictures of the universe that we've observed so far are mostly static. They're frozen in time. And instead, LSST is going to look at the southern sky roughly every 3 days and do that for 10 whole years. And by stitching those images on every patch of the sky together, we will make a movie of the universe. This is the first time we've been able to do this at this scale. And the expanded amount of space-time volume we will survey will be 1,000 times more than what we have done so far. As a comparison, I mentioned the Sloan Digital Sky Survey as a milestone in the field. A single sky scan from LSST, the thing it's going to do every 3 days, is equivalent to the entire SDSS over its 20-year lifetime. So that is the level of advance that we are about to face. So the Vera C. Rubin Observatory is named after the pioneering astronomer who established convincing evidence using galaxy rotation curves for the existence of dark matter. This is the first major astronomical facility that's named after a female scientist. I say it's about time. This amazing purpose-built facility is now taking shape. It's actually on the summit of Cerro Pachon in Chile, where the skies are perfect for observing into deep space. So LSST is going to enable different scientific missions at the same time. It's going to do detailed investigations about dark matter and dark energy, but it'll also make an inventory of the solar system. It'll look for those near-Earth asteroids that might threaten us in the future, and hopefully we can find them and have warning for that sort of thing if it's about to hit us. It'll also make this movie of the universe that I mentioned, and it'll also map the Milky Way and thereby enable additional detailed tests of dark matter models. So the resulting data set is huge. It will contain 60 petabytes of raw data, 500 petabytes of processed data. It's truly big data in terms of its volume and its rate of delivery, and also its variety. So here's a picture of where the camera will be mounted. It'll be the largest digital camera ever made. It's the size of a small truck. It will observe the sky in huge 3.2 gigapixel images. Each image will be 3.5 square degrees by 3.5 square degrees. And so that is the size of 40 full moons on the sky. So huge, very detailed pictures. This huge structure is so perfectly balanced that you can actually apparently move it with your hand without using force. So I was incredibly lucky to be able to visit Reuven last December, actually, and I joined this project in 2013, and it was truly incredible to see how the engineering drawings that we had been looking at all those years had become reality. So now we have to be prepared for this data to hit us. So one of the most amazing and powerful ways we can leverage this billion galaxy sample that we're going to get is to map dark matter with gravitational lensing. So in Einstein's theory of gravity, mass bends light. So this image behind me shows how the dark matter of a massive cluster of galaxies is lensing distant galaxies in the background. So you can see this exuberant display of multiple images and arcs. So that's really, really cool. But what we want to do is something a bit harder. And I'm going to try to show that with this demo. Okay? So can you see this thing here? This is a lens. This is not the sort of lens that you might normally see, right? It's got a different shape. So what is this shape? So if you have a massive cluster lens, for example, the potential well, the gravitational potential well of such a lens is shaped like this, all right? So everybody see this? So basically, so this is a galaxy lens. And if I go like this now across here, you can see how gravitational lensing, the bending of light, distorts a background grid, right? So you can also see, I hope, that if I hold this at different distances from this grid, the amount of distortion is different, right? Down here, we see a lot of caustics, and up here, the effect is a bit diminished. Ooh, it's pretty cool, right? So the main point I want you to take away from that is the distance between the thing being lensed and the lens matters, all right? So that's a boring grid. Let's look at some galaxies. This is a so-called Hubble ultra-deep field. So again, I can do the same. So in the middle, you can see an effect which is very similar to the actual image of a cluster lens that I showed earlier. That was also a Hubble image, by the way, right? So you can see all these weird effects and stretched out pieces. So that looks like where the main action is. But what we want to do is to measure the tiny distortions of the stuff on the outskirts. So if you now look at not the main bit, which is very highly lensed, but the galaxy is very far away from that center, you should be able to see they're distorted. And that amount of distortion, again, changes if you hold the lens closer or further away from galaxies. So that's basically the effect that we are trying to use. So in the wide field, not right looking at the barrel of the lens, but on the wide field, little galaxies get very slightly distorted in their shapes, and they also get displaced in their position. This is an effect of general relativity, and this is called weak gravitational lensing. So weak gravitational lensing, by intervening dark matter structures, distorts their shapes and positions very slightly. And if you knew where the lensing matter was, and if you knew where the source galaxies are, you can invert this effect to work out maps of dark matter over cosmic time. Okay? So the amount of distortion is related to the distance that light has traveled to us. And by measuring the distortions, you can map out the dark matter over the history of the universe. But if you didn't know quite how far away the foreground lens mass is compared to the background galaxies that are being lensed, you will get a wrong impression of the growth of cosmic structure over cosmic time. And by doing that, you will conclude that you have got a wrong cosmological model. So again, we've come back to this issue that we can't really work out distances very accurately in the universe. And that's similar to the issue that Hubble faced when he was trying to work out how far away the closest big galaxy is. But now we're trying to do this 2 times, more than 90% the age of the universe. So that is really hard. So let's try to think about how we can work out how far away things are. So I've got another demo coming up, but first let me just remind you about rainbows, okay? So this is a picture of a rainbow that I took in Iceland some years ago. You've probably seen quite a few rainbows recently because we've had all this wet weather. So, what's happening here? There are little particles of water in the air, and that is splitting apart the colors of sunlight. So basically, sunlight is characterized by a whole bunch of different constituent colors which correspond to different wavelengths. So this graph illustrates how the light from the sun is distributed as a function of wavelengths. And so the redder colors are associated with larger wavelengths, and the bluer colors are associated with smaller wavelengths. So I couldn't bring the sun into this room, but I've got a small bulb here. Let's see. Have you all got a diffraction filter? Okay, so what I'm going to do is I'm going to take this around. Could you please look through the diffraction filter? I will do it a couple of times. All right. Did anyone see a rainbow? Put your hands up if you saw a rainbow. Yay! Okay, good. So we have seen some rainbows. That's really cool. And where did my clicker go? Here it is. Okay. Oh, that's the wrong one. Okay. So let's see if this works. So that is the spectrum of an incandescent light bulb. It's not quite the spectrum of a star, but it's got this featureless kind of distribution as a function of wavelength. If you looked at the sunlight, you would probably see more yellow colors, but this bulb would have shown you more redder colors. okay? And so now we are going to look instead at a hydrogen light bulb, which Judith here is going to come and operate because I'm a bit of a klutz and I don't want to make a mistake with this thing. So she's going to turn this around. It's only going to be on for 30 seconds at a time, I believe, so please be fast and look through. She's going to do a couple of rounds, I think. Please go ahead, Judith. Don't worry, it'll come to both sides, so she's going to do it a couple of times. All right. Is anyone still seeing rainbows or not? No? Something else, huh? Okay, okay. I think that's probably enough. Thank you so much. Thank you, Judith. Right. You shouldn't have seen rainbows. You should have seen 3 lines. One is red, and one is blue, and one is kind of purple. But the red one should have been the easiest one to see. All right? So this is the spectrum of a hydrogen lamp. And what you saw is the so-called Balmer series, which is one of the quantum mechanical transitions of the hydrogen atom, okay? So that is a key piece in the puzzle of working out how far away things are, because spectral lines like this are critical to measuring what we call redshifts. So in the laboratory on the Earth, we know exactly what is the wavelength of each of these transitions. It's purely determined by quantum mechanics. And so when we look out at distant galaxies, so galaxies are full of hydrogen, you know. This is one of the elements that we can use to do this exercise. You know, most of the atoms in the universe is actually hydrogen. Did you know that? Most of the rest is helium. And whatever's left, it's only about 2% by mass. And so, you know, all the carbon that you're made of, or the oxygen you're breathing, that's in a small minority there. And so astronomers call all of the rest of the periodic table, other than hydrogen and helium, metals. It's like, okay. Anyway, hydrogen is abundant in galaxies. So we can measure these lines out there in the distant universe, and you can measure them in further and further away galaxies. And you see them shifted to the red. Why is that? Because in an expanding universe, the wavelength of light is stretched out by the expansion, or it's redshifted, because longer wavelengths are redder, right? So we can measure these lines at the wavelength they've been redshifted to, and we know what is the reference line location in the laboratory. So by comparing those two, you can work out how far away those galaxies are. So is this case closed? Is this what we need to do if we have billions of galaxies? Can we just take a redshift from each of them by measuring its spectrum? Sadly not. The answer is no. With current detectors and current technical capabilities, despite the availability of huge facilities like Rubin that we are constructing, we can't get a spectrum for each galaxy in that billion galaxy sample. Instead, Rubin will measure just 6 colors per galaxy. Okay? So we have to make do with these 6 colors, and we have still got to measure the redshifts of those galaxies with the 6 colors. So in the past few years, a key realization has dawned. To decode the cosmos, we need to understand galaxies. Now that strikes fear into astronomers' hearts, because galaxies are complicated beasts. They're among the most complicated objects in the universe. So understanding their light distributions is related to understanding their constituent populations of stars and other stuff they contain, like gas and dust. If we could bring the lights down, please. Imagine you had a recipe for generating realistic examples of galaxy spectra and colors. What ingredients would such a recipe contain? The light that galaxies emit depends on their physical properties, like their mass, their star formation history, their dust, their gas, their metallicity, whether they've got quasars powering them, and their redshift. So there is such a recipe that allows you to predict colors of galaxies. This is known as stellar population synthesis. We can leverage this to solve the challenge that we want to solve. We can bring the lights back up now, please. So the idea is that you can work out how far away galaxies are if you solved another and seemingly harder and more general problem, which is to be able to model faithfully the diversity of galaxy properties in the universe over cosmic time, simultaneously with the redshifts. This problem is not tractable with traditional methods. When you consider even current catalogs of hundreds of millions of galaxies that we already have, let alone LSST's billion galaxy sample. So modern machine learning methods can accurately describe the complicated web of interdependencies between galaxy properties, and these tools have literally become available in the last few years, essentially over the pandemic. When we were all locked away, AI technologies were being developed, and they have arrived just in time. So we've just succeeded in the very first attempt at doing this, where the recipe for making realistic galaxy population is actually encoded within an AI technology, which is called a diffusion model. I don't want to go into technical details about this, but this is essentially a flexible mesh that lives, in this case, in 16 dimensions. And those dimensions describe the ingredients that go into making galaxy colors. I can't imagine 16 dimensions in my head. I'm guessing you can't either. So I've got a toy model here where there's 2 parameters describing the population of galaxies and 2 parameters describing the data. So we can make a realization of the population of galaxies by drawing from this diffusion model. And then we can compute the observable properties of galaxies. And then we can add noise and selection. And by selection, I mean, in a given survey of galaxies, you can't see every object that's out there in the universe. At the end of the day, your detector will have some sensitivity limit. And so you have to work out which galaxies you could have seen in your survey. So when we add all of these ingredients together, we now compare them in the space of data. And in this case, the calibration survey that we are fitting this to has 26 dimensions. So imagine 2-point clouds that are in 26 dimensions, and we are trying to make them the same. And we do that by comparing something called an optimal transport distance. And we're trying to make this distance smaller and smaller as this model is training in this way that machine learning models get trained. And at the end of the training, we go back to the diffusion model, and now this mesh has deformed such that you can now take away everything else. It's now become independent from the data set it was fitted to, and it now makes realizations of real galaxies in the universe, and you can draw from it, and you can mimic any other survey that you want to, including LSST. So with tools like this at the ready, this is what we can look forward to starting next year. Here you can see a typical patch of the sky. On the left-hand side, it is the Sloan Digital Sky Survey's image of that sky. And on the other side, it is what we can expect from LSST. You can see the great amount of extra detail, the number of galaxies that you can see in the same patch of the sky now with LSST quality data. And so in 100 years, we'll have gone from knowing one external galaxy existed to measuring 1 billion galaxies. So powerful machine learning technologies have become available just in time to do some heavy lifting here. These tools will help us embrace the complexity and the size of the data set rather than fighting it. And we can use them to help us decode the cosmos. So that was the first technology that I'm going to show you. And now I want to switch to a complementary approach to decoding the cosmos, which is detecting dark matter in the lab. A key unanswered question in cosmology is, what is the dark matter particle? There are many, many creative theoretical proposals. Theorists are very creative, but there are two broad candidate theories that are very compelling. Weakly interacting massive particles, also called WIMPs, and also axions. These are particularly attractive because they solve major problems in particle physics. They were not invented to be a dark matter candidate, but just by the by, they are also compelling dark matter candidates. And much of the experimental effort in the past decades has, for various reasons, mostly sociological, I think, but also because of the experimental difficulty, people have focused on the WIMP hypothesis, and it's only more recently that experimental attention is turning into axions. So much of the WIMP parameter space is already mostly closed off, but there's a huge part of the axion parameter space that's relatively unexplored. So the so-called QCD axion is my favorite dark matter candidate. This is a compelling candidate because it was not invented as a dark matter candidate, but rather to solve mysteries relating to the standard model of particle physics, in particular the so-called strong CP problem. Again, I won't go into technicalities, but basically there is a free parameter in the standard model of particle physics, which is the neutron's electric dipole moment. And this could take any value, and then they went and measured it, and they found that it was tiny. So this is an indication of fine-tuning, and physicists don't like fine-tuning. So the axion was proposed as a dynamical way to explain this fine-tuning, and it was meant to wash away the problems of the standard model of particle physics. It's actually named after a detergent. So this type of dark matter behaves as a wave as well as a particle. So its wave-like properties are related to its mass. So one of the problems with hunting dark matter is that we don't know exactly what is the mass of the dark matter particle. It can often range over many orders of magnitude in mass. But each mass has a characteristic wavelength in the case of the axion. So how can we detect this? The axion has a very weak coupling to photons, particles of light. An axion can decay into 2 photons. We could wait for several times the age of the universe for that to happen, or if you're very impatient, we need to try something else. So one of the things that we can do is we can pump many photons into a very strong magnetic field placed into a small cavity. So now you got this cavity, you've pumped a lot of photons in there, and now we can have many, many chances to see the decay, right? So we need many axions in a given volume so that there is a reasonable likelihood to observe the decay. And when the decay happens, we get a teeny tiny electric current, which we can read out. So detecting the axion is a little bit like tuning a radio. So here's a radio. So let's see if I can find. Okay, so, imagine an experimentalist looking for the axion. Most of the time, they'll just see the noise in their experiment. And then if you can tune it, remember, when I tune it, I'm changing the frequency and hence the wavelength. And I pick up a signal. The axion sounds very beautiful. Okay. So hopefully you got the point that basically we need to tune to the right wavelength to see the thing. So, but we don't know which wavelength range to tune over. To get this detection and this spike in the electric current, we need to have the effective wavelength of the axion match the effective wavelength of the photon, and that needs to be the size of the cavity. So you see, there are three things that need to match. The size of the cavity needs to match the size of the photon wavelength for that axion wavelength in order to get this resonance that leads to a peak in the power. So you can already see a problem, right? I said that the masses can range over orders of magnitude. And so are we going to build different cavities for every single mass? That's really difficult. So this is like I've restricted myself in this, sorry, what is this? The radio, I can't now tune to find the station. I can only look over a very, very narrow range of frequencies. And if I don't find the station there, that doesn't mean the axion doesn't exist. It just means it wasn't there where you were able to build the cavity to look for the thing. So this was a conundrum for a while. And higher frequencies actually probe larger and larger masses. And for the QCD axion itself, the larger masses are the ones that are theoretically preferred, but also experimentally the most challenging, because larger masses and higher frequencies are inversely linked to the volume. So to probe higher frequencies, you need smaller volume cavities. But then you can't pack enough photons in there to get a signal to be read out, because even if you put this into a 10 Tesla magnet, which is very powerful, you just don't have enough boosting to get an electric current that you can read out. So this was a huge problem for a while, but a few years ago, we came up with a fantastic way to crack this. And that's by changing the relationship between wavelength and frequency. So you are allowed now to take the same effective wavelength for the same size of cavity, but by breaking that relationship, and this is done by giving the photon an effective mass, you can actually probe higher frequencies and larger masses with the same size cavity. So the key idea is to give the photon an effective mass by using an effective medium called a metamaterial. So now this sounds like, okay, metamaterial, what's that? Okay, it's just you take a shape, right? This is my cavity, and instead of having a volume that shape, you basically replace it with a bunch of vertical wires, right? That is a wire metamaterial. So that's literally what it is. It's replacing the shape, the geometry of the cavity by something made of wires. So, a metamaterial is essentially a composite material with different properties to its individual components, and that's what this is. So you can change the effective mass of the photon to obtain the resonance, rather than changing the size of the cavity, which you would have to do for zero mass. And because we have these wires, it's also solving another problem, because you can now tune. Here's one tuning idea. You can change the spacing of the wires, and that makes your cavity now suddenly sensitive to different wavelengths. So with the same experiment, you can tune over a range of masses. Here's another tuning idea. Through the rotation of shaped wires, which we are calling sails, and these tuning possibilities mean we can now scan over a range of axion masses with one experiment, rather than being limited into a very narrow mass range. So this idea was very popular and took off, so we actually got funding to build this thing. We are currently experimenting with different wire metamaterial resonator prototypes. This is a PhD student at Berkeley, Heather Jackson, with the prototype that they're building. And this is our Stockholm PI Jon Gudmundsson in the lab working with the postdoc Gagandeep Singh. They have a different prototype design. Note that they are truly tabletop experiments. The magnet facility is also the size of a university lab, say, probably even smaller than this room we have here, in contrast to the truly gargantuan particle physics experiments that one usually encounters. So we call this experiment Alpha. It's currently under construction at Yale University, and it will take data for 5 years. This will allow us to probe the most compelling range of masses for the QCD axion. So the next few years will be very exciting for axion dark matter. So in the last few minutes, I want to go back to the beginning of the universe. This is the most far-out thing I'm going to show you. So I seem to have lost this. Let's hope this works. So I want to show you a mind-blowing implication of inflation, which, remember, is the prevailing paradigm for the formation of structure in the universe. If this is a correct description of nature, inflation doesn't just make our observable universe. It makes a much bigger universe than that, and that's not the end of it either. It will form structure on scales vastly bigger than the size of the observable universe. It will make many universes. It will cause bubble universes to form, and our universe is just one among those countless others. So in this picture, most of space, on scales much larger than the size of our universe, is trapped at high vacuum energy. So imagine being in a landscape of potential energy, like this picture of the Torres del Paine range in Chile. You can tell I've recently been to Chile. So there's you're now at the top of this mountain, and as you probably know, if you climb a mountain, you gain potential energy. So now you're at a place of high vacuum energy, and that's what causes space to inflate. But there's the possibility of tunneling to a place with small vacuum energy, like the lake, right? And if you are in a place with small vacuum energy, you tunnel there through the formation of a bubble of the lower vacuum energy, and that causes inflation to end locally. So that's a bubble universe. But most of space is still trapped on the top of the mountains. So this could have been the birth event of the universe. Sounds like science fiction, right? The main hurdle to testing these kinds of ideas, even in principle, is that our understanding of the relevant theory is just not good enough. These are very difficult calculations. It's as if the universe said, here's all the possible hardest maths that you might need to describe nature, bundled it all up into one problem and told physicists, yeah, you figure that out now. There are many assumptions and approximations that are involved, and we don't know which are the right ones and which are not quite right. So a new approach that we are taking to understand this theory better is to emulate the same physical equations, but translated within an experiment in the laboratory. So by comparing our maths With the experiment, we can refine our theoretical understanding and we can work out which approximations are valid and which are not. So basically, the idea is that you have one system that you can't experiment with. That will be the early universe. And there's another system you can experiment with, which, under the right conditions, exhibits the same phenomenology described by the same physics as the original system. So if you can work out what those right conditions are for the physics to match, you can translate the understanding gained in the laboratory back into the system that you can't experiment with, which is the early universe in this case. So we are currently building in Cambridge a prototype in the lab which behaves like a quantum field undergoing vacuum decay. So this quantum tunneling phenomenon that I tried to explain earlier. The experiment involves macroscopic collections of ultra-cold atoms called Bose-Einstein condensates. This experiment operates just above absolute zero. Our laboratory universe will soon be transported into that little blob called the science cell where data taking can begin. I mean, it's a very messy experiment, but I think it's super cool. Unfortunately, this was hard to transport into the Royal Institution. I'm very sorry about that. But I want to show you a system undergoing a phase transition right here in this room, which also has a non-trivial link to the physics of the early universe. So I now have my magician friend over here. So this is going to be our laboratory experiment and analogy, okay? It is a Tibetan singing bowl, and he's now going to do the thing and make it sound a note. Can you hear that note? So it's a single note, right? It is the resonance frequency of this bowl. Very good. Let us proceed with the water. He's now going to put some water in here. All right. So let's repeat the rubbing. So you can still hear a note. It's slightly different. Do you see this? Do you see this? Isn't this cool? So the rubbing excites a resonance of the bowl, and it causes waves of water to form, which then crash into each other, and then it's fizzing with these bubbles. You're presumably familiar with boiling your kettle in the morning to make a phase transition happen. Yeah, to make a phase transition happen in your kettle, you gotta put some heat in, right? So you boil the kettle, it goes from being liquid to being a gas through the formation of bubbles of steam, right? Here, we did not put any heat in. We had what's called a parametric resonance. The small vibrations on the singing bowl excited the water so that a small periodic variation caused a huge amount of stuff to happen in the system, causing these water bubbles to actually pop out in a phase transition. So, I think this is one of the coolest demos I could think of. But, it's not just a cool demo. There is a process that we think also happened in the early universe through parametric resonance, which is particle production. And this happened after the end of inflation to turn the energy in the inflaton field into the particle and fields of the standard model. So, that analogy is not as tight as the one we want to do in the lab. We really want to emulate quantum field decay in the lab. And so that is what we're planning to do. This is a fairly unique collaboration at the intersection of two fields that rarely come into contact: condensed matter experiment and cosmology theory. Even just thinking deeply about this problem before we have data to compare with has led to advances in the understanding of the theory beyond the standard approaches that were available up to that time. I can't yet show you analog bubble universes nucleating in the lab, but I can show you computer simulations of what the bubbles would look like in the experiment versus our best understanding of what happens in the early universe. And by tuning the experiment in different ways and by turning the analogous blobs in our mathematical calculation, we can see whether our expectations are correct. I mean, this is a bit like, we can work out if we got a larger Tibetan singing bowl or put more or less water, we can see what happens to the bubbles fizzing, and we can try to work out why those things are happening and work out observations that we could possibly make about that system. It's the same. So we want to be able to work out, by changing parameters of the experiment and observing the output, how to make that mathematical prediction for that experiment correctly, and then translate that same understanding into the early universe. So I want to end by emphasizing that understanding our universe requires interlinked progress along many different frontiers. The field is being driven by technological innovation. I think I showed that. This is producing large volumes of varied, complicated data, which we need to model accurately and to contextualize in terms of fundamental theory. I hope that I managed to convey an impression, at least, of how the interplay between theory, observation, and experiment work together and plays out to support a synergistic understanding of the universe. And I've also hopefully motivated some of the younger members of the audience to join us in this quest to decode the cosmos. Thank you very much.